Assalamu alaikum warahmatullahi ta'ala wabarakatuh, ladies and gentlemen. Welcome back to another live stream. Let's go. Okay. So, last live stream we have got Vulkan triangle. Now, I'm not honestly sure what we're gonna do in this live stream, but I think what I would like to do is to use dynamic rendering with Vulkan 1.3 and maybe also buffer device address and like use buffers and GPU allocator, etc, and maybe even HLSL, but we'll see how it goes. Either way, let me actually share the live stream. Copy video URL. Okay. Let's go. Alright, I shared the live stream on my Discord server, and please join my Discord server so you can get notified of new live streams, and you could also vote on next live streams. Marty Flowers, hello, welcome back, long time. Welcome. Alright, glad to see you here today. Great, okay. So let's see where to even start with this now. Let's see. Okay, we're gonna try to use dynamic rendering. Now from this live streaming on, I don't know exactly what I'm doing. It's like, at least like in the previous live streams, I had a little idea of what I'd like to do and how to do it. But in this next live streams, you're just gonna basically see me learn and just try things until it works. Hello Naji Habidi, welcome to the live stream. Welcome. Okay, so all right, so I think first of all we probably gotta check out the spec. I think let's see the spec for dynamic rendering. This is gonna be fun. Hopefully, I don't know. Let's see. Vulkan dynamic rendering. And by the way, we're gonna be using Vulkan 1.3, and we're not gonna care about any other platforms other than desktop. Basically, Windows and Linux. We don't even gonna care about Mac OS. In fact, we don't care about them anyway. Though before that, let me make sure to select version 1.3, which I actually did in the first live stream, but then I removed it. But right now, I have to get it back. Okay, so let's see. In the instance. Where is it? Builder, enable extension names. Nice. So here I gotta add the application info, I think. Let's see. No, not here. Application info. There you go. And let's add application info. Okay. And here we're gonna get the builder, and we're gonna give it the application or the API version, pretty much. Let's go, and VK API version 1.3. Let's go. We're gonna be using the latest extensions. Well, in fact, since we're using Vulkan 1.3, dynamic render isn't really an extension in this version. It is in the previous versions, but like in Vulkan 1.3, it's promoted to core, which means that we don't really need to enable any extension to get it. It's already in the actual API itself. But we still have to actually enable a feature, a GPU or a device feature, to actually be able to start using it, which is what we're going to do right now. So I'm going to be using API version 1.3. Let's go. Next up is probably the device, okay, or the physical device. Let's see. Okay, where is it? Swap chain name, cool. Builder, enabled extension names. Okay, let's try to add features here, maybe. Enabled features. Oh, oops, not that. We're gonna be using the functions. Okay, enabled features. Oh well, I'm recording at night just to avoid these stupid motorcycles going in and out. But well, somehow I have no idea. It's crazy. It's like a motorcycle just spawns in Morocco when you start streaming. even if you're streaming at like 1 a.m. like at night, it's just I have no idea. Anyways, oh well. What can I do? Okay, so physical device features. Let's go ahead and do this builder, and let's just see depth bound. Okay, let's try to look for dynamic rendering. Oops, what is it called? Interesting. So these are all the features that we could actually enable, well, as long as the device actually supports it. By the way, is the voice fine, and also the the video quality too and stuff? Let me know. And if you noticed, I actually have disabled the NVIDIA RTX voice, so you'll be able to actually hear background noise and stuff, and the keyboard. Let me know if you like that or not. Otherwise I could actually enable it and you won't hear those. But anyways, let's see, shooter storage, depth clamp, drawing direct. Okay, let's actually check the spec. And let's see how it goes. So VKKHR dynamic rendering. All right, let's go. Where can I find let's actually go to Vulkan, or we could just check dynamic rendering. I remember there's like a cool blog post that we could also check out first. Try that first. So here he's enabled device extension. We don't need that because we're using Vulkan 1.3. What's next? Yeah, let's see, device creates info. He's actually using pnext. Let's go. All right, so I guess let's try to use this pnext, and basically we need this VK physical device dynamic rendering features KHR, though we're not gonna need KHR because we're not using the extension, we're using the core API. Okay, dynamic rendering feature. Okay, lovely, and then we just enable that. Okay, cool. Let's see, so we don't really need this guy right here. So we need pnext, in fact. How we can do that? I remember, yeah, there's push next. Prepends the given extension struct between the root and the first pointer. This method only exists on struct that can be passed to a function directly. Only valid extension structs can be pushed into the chain. Okay, lovely. So let's actually push next, and let's push a reference to a VK device, I guess, feature, physical device, dynamic feature, physical device, dynamic rendering features, is it? I would guess. There's KHR. So yeah, and let's just, I guess, do this builder dot and dynamic render. Let's go, and then we just enable it like this. Dynamic rendering. Okay, great. What's happening here? So it expected a mutable physical device dynamic render features builder, but found that, can we change reference to mutable? Yeah, we can. So that's nice. All right, let's see if this actually works. So this should enable dynamic rendering. Okay, lovely. So everything works out just fine for now. Now we actually gotta be using it. Now we have just enabled dynamic rendering. Now we gotta use it. Let's see. So I think basically, first of all, we can actually right now throw the render paths and the frame buffers in the trash bin. We don't need them anymore. So render paths, there you go. This whole thing goes into the trash bin. And the other thing that would go to the trash bin is yeah, so you don't need to pass a render pass. Just say vk render pass null now. Welcome to dynamic rendering. Null. And what else? We also gotta add a pnext to this one too. So let's push next. you go. And let's see what we gotta push next to use dynamic rendering command buffer, blah blah blah. Where's the pipeline? Pipeline. There we go. Pipeline creation. You gotta add vk pipeline rendering create info khr. Okay, so a reference to, well, a mutable reference to a vk pipeline. What is it called? Rendering. Create info. Let's go. Builder dot, and let's see what we need. We need the format, I think. Yeah, color attachment formats. We don't have any depth or stencil right now. We only have one color attachment. So, and let's just basically say from ref. So basically, instead of passing the render pass, we're gonna be like just giving the format directly here into the pipeline, and so that's pretty cool. So we don't like repeat ourselves in the render pass and in the pipeline, etc., etc. Okay, so now I see the vk format, bgr8 srgb. Let's go. I probably need to put that into a variable, honestly, at this point. But anyways, okay, cool. What's happening here? Format by found. Oh yeah, let's use from ref because this is expecting a slice, but I only want to give it one item, and this should be a reference, of course. So we're basically creating a one element slice from a reference. Okay, cool. What else? So we gave it the color attachment formats, and I think that's pretty much it. What else we could give it, by the way? Just to see, color attachment formats, color attachment depth, yeah, pretty much. And there's a view mask. I'm not sure what's that. We could check it out later on. Anyway, so that's pretty much it for the pipeline, which is lovely. The other thing that we actually gonna need is, let's see, use dynamic rendering in command buffer. Basically, we gotta use vk-cmd begin render pass. Oh, actually, instead of begin render pass, we gotta be using this rendering info khr struct and this stuff right here with vk-cmd begin rendering khr instead, which is pretty cool. Okay, let's go ahead and see what we can do. Oh, by the way, yeah, we also don't need frame buffers. Put that in trash bin too. Welcome to dynamic rendering. What else? Okay, create fence. Yeah, so we don't need begin render pass anymore. We could just use cmd begin rendering, I think. Rich. So begin rendering, and we gotta give it the command buffer. There you go. And then the rendering info, which we could provide here. So vk rendering info, builder dot, and let's see. So we need the render area, which is basically, hold on a second. Let me add the semicolon there, so to stop crashing up. Let's go with direct 2D, and yeah, let's just use builder. Oops, what I'm doing. Direct 2D. There you go. Builder dot, well, what, extent. There we go. And for that, we could just use vk extend 2D. Oops. And then there's width and there's height. So for the width would be window size. Well, what? Where's the width coming from though? Weird. Where's the width coming from? No idea. Can I actually access window size here? No, cannot. Interesting. Okay, let me check where I put the window size. There you go. Okay. So, do I actually even use it at this point? Yeah, I still use it for the pipeline. Cool. But you also need it here in the command buffer, seems like. Do we actually really need that at this point, honestly? I wonder. I don't think maybe, not sure. Let me see real quick. Where is the pipeline again? Pipeline. Yeah, no, it's not telling me, but we could try it out later and see if that's really needed or not in this case. Okay, event loop run. So before this guy, let's just grab the window size pretty much, and let's use that. I think width comma window size well, I guess I just gotta basically say this window size dot width, and then the height window size dot height. What about that? And let's actually build it. Right, build it. Sig STKFLT, welcome to the live stream. Welcome. How's it going? Right, so we're basically just using dynamic rendering so we can trash the render paths and the frame buffers, basically in Vulkan 1.3. Just finished midterm week. Nice. Okay, so right, I think we got this render area. Now let's check out the other ones. Render area, there's also layer count, which I believe would be 1. We're not using any stereoscopic stuff or whatever. Flags, I don't think we need flags. What else? There's render area, flags, color attachments. We do need this one. So basically, instead of creating frame buffers and recreating them, etc., you just, you know, like you give it directly inline instead of going crazy about that, which is amazing. Okay, let's go with the color attachments here, and let's say this vacay rendering attachment info. Okay, and well, in fact, hold on, this is a slice, so we actually gotta say from ref. And then we could say this vacay rendering attachment. Hold on, there you go. Builder, oops, builder dot, and then okay, we gotta fill up this stuff that we have filled in the render pass before. Okay, cool. So alright, let's start with store op, I guess, or let's see image view. Okay, let's start with that. So the image view would be, let's see. So we got the image index. So I think we could basically say swap chain image view. So as you can see, we don't need any frame buffers. You just give it the swap chain image view directly. So swap chain image views, and then we're gonna need the image index. There you go. What's happening here? Oh yeah, as view size. Okay, cool. Okay, what's next? That's the image view. Now we gonna need, let's go with store op, why not? Vacay attachment store op, and we actually want to store the results of the rendering. Okay, Lloyd op, which is basically reading. Well, do we want to read it, or like what we want to do at first? Basically, Lloyd op. Well, we're gonna clear it basically with the color, clear color. And what else? Lloyd op clear value. Okay, we could also give it right now the clear value, which is basically gonna be clear value builder. Oops, what? Cannot actually give it builder or what? No, we cannot. Interesting. Huh. So there's default. So basically seems like you gotta give it like color which is a clear color value. Then do you have depth stencil, clear depth stencil value? Well, for now, can I say default? Yeah, okay, cool. I don't really care about it right now. And there's the image layout. Well, for the image layout, I don't actually remember what we did exactly. Let's see. Don't waste time here. Where's the render pass that we had? Okay, there you go. So the image layout, I think, was in define, I guess. Hello HGKL, welcome to the live stream. Hello. How is it going? Image layout. Okay, so like, what is the image layout currently, I guess? Well, can we just say, I guess, in define, maybe? At this point, and what else? Or hold on, like, what it means exactly here? Maybe we gotta say color value, I guess. Yeah, I think we gotta say color attachment optimal instead. Okay, what else? There's also resolve image layout and resolve image view, which we could actually use for MSAA later on. We want to add it. Are we using Ash or Volcano? Ash. We're using Ash. Ash binding. Raw Vulkan. Okay. Resolve mode S type. Resolve image view. Clear value. Okay. I think that's all we need, really. I mean, hold on, we have actually an example here, in fact, which is nice. So color attachment info, image layout, there you go. Image layout, attachment optimal KHR. What? Attachment optimal KHR? Okay, just using this for some reason. I wonder, like, what is the difference between these two? I'll just go with this for now until we have a problem. Okay, what else? Did I miss anything? Lloyd OP, yeah. Store OP, let's go. Clear value, yep. Vacate render info. So now I think we just gotta, yeah, we're already beginning the rendering. So yeah, that's pretty much it to, I think, to begin rendering. Do we need anything else? Like, does this return like an error or something? I would guess, yeah. Ash device and save FN. What? Where's the? I guess it doesn't return anything. Anyways, so device. Now let's actually end that. Well, so before we end the command buffer, we gotta end that basically. So end, or is it end? Yeah, end rendering, I think. There you go. CMD end rendering, and give it the command buffer. And yeah, that should be it for that one. Begin rendering and end rendering. Lovely. Okay, what else? Pipeline creation, we have already done that. Yeah, and now we actually have to do the image layout transition stuff. Because, well, the render pass was actually doing something for us, which is the transitions of the image layouts. Right now, we don't have that luxury anymore. We gotta actually do it ourselves manually using image memory barriers, which is honestly much more intuitive and, you know, much more coherent with the API instead of just that render pass magic. So yeah, but let's actually see just what's gonna happen right now. Is this would even work out at this stage, like, or do we really need? Because last time, wait, we are using dynamic rendering. We were using a render pass and like just normal Vulkan, but right now I'm trying to basically convert into dynamic rendering right now with Vulkan 1.3. Okay, we have an exception. Interesting. So in the end rendering, for some reason, oh yeah, let me grab my validation layer stuff. Where is Vulkan configurator? Okay. Let's see, validation, and let's see what is wrong. There you go. Let's go back to the console and let's see what we got. Okay, pretty cool. So what is going on? This is just an info, and we have two errors right here. yeah, in end render pass. Oh, end render pass. Oh my god. Okay, gotcha. So I forgot to remove this end render pass here. Okay, what else? Let's see what's gonna happen now. Oh my god, it works already. Interesting. Okay, so it actually works already without the image transitions, but of course to actually do it properly, I mean, it's like it's not perfect according to the specs, so it may work, it may not work. In my case, it worked without even the layout transitions, though maybe it could be that there's some performance penalties or something like that. Either way, we gotta actually go ahead right now and actually use the image memory barriers, I think, or something like that, to actually transition the image layouts manually. Okay, let's go ahead and do that. So basically, before the begin rendering, I think we gotta actually do that. All right, let me check this blog post. So begin dynamic rendering here, there you go. And before that, we need to actually basically switch the image layout from what is it, I think from indefined to, yeah, from indefined to color attachment optimal, basically. Okay, cool. So let's actually do that. So device dot, let's see, device dot cmd pipeline barrier. There's also two. I'd like to use synchronization too, but for now let's just stick to the first version, and then later on, so we could, you know, like go step by step and recognize what is the problem exactly, instead of going all in. Okay, so after this, I'm probably gonna try to use like the newer synchronization 2 features and like functions. So yeah, SRC stage mask, pipeline stage flags. Okay, so which stage we should wait for? I think no stage at this point, or is it? No, this is the destination stage. Well, we gotta need, I think, color output. Is it? Hold on, what is this exactly? Oops, this is SRC stage mask. What even are the differences between the normal functions and the functions postfixed with 2? Well, the functions postfixed with 2 are like the new synchronization functions in Vulkan. Like if you're using Vulkan 1.2, I think, or greater, or we're using Vulkan 1.3 right now. It's actually in the core API at this point, though if earlier, you're going to be enabling an extension and using that instead if you want it. And of course, if the device supports it. But in Vulkan 1.3, of course, it's probably mandatory. Let's check it out, I guess. So Vulkan synchronization 2. Though there's not a lot of resources about it. I tried to find, but there's really not a lot other than, of course, the spec and something here and there. But anyways, so you can see that well, it promoted to Vulkan 1.3. So yeah, if you're using Vulkan 1.3, this is basically in the API itself, in the core API. If you're using something like a version, earlier version, then you gotta be enabling as an extension if you want it, and if the device actually supports it. So yeah, so this extension modifies the original core synchronization API. So we're gonna get back to this later on, though. Let's now focus on dynamic rendering, hopefully. Okay. So the source stage mask, let's see what the blog post is doing exactly with that. Source stage mask. It's basically, I think, keeping it as 0, right? Hold on. Oh, top of pipe bit. Okay, so top of pipe bit. Let's go. Vacate pipeline stage. Ooh, my bad. Vacate pipeline stage flags. Let's go. And top of pipe bit. Though, by the way, even this one I think isn't really in like in earlier Vulkan versions. Maybe, I don't know. Not sure. Anyways, destination stage mask, and here vacate pipeline stage flags. Okay, what it done here? Yeah, color attachment output. Color attachment output, and then we're basically given zeros to the other ones, other than image barriers, basically. So we don't want any memory, any dependency flags. So what we gotta do here, well, dependency flags empty, I think. And what else? There's memory barriers. I think we don't need any memory barriers at this point, so let's just give it an empty slice. And how are we gonna deal with that, or how can we do that? I don't know, honestly. I guess maybe like this. I mean, I guess that seems to be working. I use a lot of languages, so it's hard to actually remember everything about a language. Okay, cool. What else? Now we need image memory barriers. Now this is what we want. Basically, it allows you to like specify all these barriers if you want them to, but we only need the image memory barrier here. We only need one, so I'm just gonna use some ref instead of a slice. And here I could give it the image memory barrier. Okay. So basically, memory barriers or image memory barrier would basically like, or pipeline barriers in general is like used for synchronization. It would essentially not allow a command to run or some stage to run until what is like before it reaches some certain stage. So, and also it at the same time it like can transition the layout of the image, for example. So that's useful to make sure like before the command, for example, begin rendering access the image, it's already the image is ready, you know, at the exact like at the proper stage, etc., etc., and also at the proper layout. But anyways, so now what we gotta do here, builder, right? And what's now? Of course, the image. Now here, are we transitioning the layout or the swap chain image? We're transitioning the swap chain image layout. So we could use it with the command begin rendering, because at this point, the layout is undefined, and to actually be able to render to it, we gotta need it in color attachment optimal layout, I think. So that's basically what we're doing here. So yeah, we're gonna access the swap chain images at the index that we got from acquire next image. Basically the frame that we're, or the image that we're working on currently on the swap chain, basically. Okay, image index as usize. Okay, what else now? That's the image. Next up, let's go with the initial layout, I think, or what is it? Yeah, old layout. So the old layout, I don't care. Image layout undefined, I think. And the new layout that we want to transition to is image layout color attachment optimal, I think. Let me just make sure that is the case, because I'm not the best at synchronization yet, though I'm getting there. I'm starting to understand more and more every time. Okay, so as you can see, undefined the first layout, and the layout that we're transitioning to is color attachment optimal, so we can render to it. Lovely. Okay, what's next? There's SRC access mask, destination access mask, blah blah blah. There's also queue. Yeah, you could also transition from one queue family to another. For example, like if you have the presentation in one queue family, and then the graphics queue is another queue family, then well, you could use this to transition the image ownership, I think. Unless maybe if you use like concurrent access, I think, or something like that. It's kind of crazy, but anyways, we don't really need to worry about this now. The source queue family index is 0, and the destination queue family index is also 0. Though as it's 0, we could probably leave it as it is, but maybe that's not too wise. Let's just explicitly give them. Let's see, where is it doing it though? Yeah, it's not actually giving them because, well, they're just zeros. So honestly, yeah, fine. Let's just remove them for now. And what else? Now we also need the destination access mask. And I guess the SRC access mask is basically 0. Yeah, probably. So let's see the SRC access mask. Oopsies, let's go. And access flags. Let's see which one is actually 0. I think it's basically empty. Yeah, probably pretty much empty. So basically we don't really need any actual access in terms of the source, pretty much. So we don't even need this at this point. But the destination access mask, we need that. And what it is, it's vacate access color attachment right bit. Basically, here's how it works. So we're not waiting for any access mask, so there's no SRC access mask. But for the destination access mask, we're basically telling it that we're about to write to that color attachment, to that image as a color attachment, I think. So yeah, access flags, color attachment, write. So there's write, read, and also read non-coherent, which is part of an extension. Okay, cool. And I think that's pretty much it, maybe. There's also sub-resource range, my bad. Okay, let's actually set that to sub-resource range, blur, and layer count, as always, 1. And level count 1. And aspect mask, let's go with that, I guess. Oh, what's that exactly again? Yeah, color pretty much, I think. And yeah, though this needs to be like a reference, I think, so we can build it. Well, expected image sub-resource range, found sub-resource range builder. Oh, it actually expected not a reference but an actual value, so let's actually build it manually. There you go. Cool. Is it color, by the way? Yep, it is color. And yeah, that's pretty much it for the sub-resource range. Too simple. So I think that's pretty much it for that one, probably. Did we miss anything? I don't think so. Yeah, pretty much none. Okay, now we got another thing to do. Oh my god, hold on a second. There's actually 2. There's the first one where we actually like transition it to color, and the second one, which is to transition it to presentation. Well, what is this? This actually, yeah, transition it into color attachment. Great, which is correct. So now pretty much we're gonna have a similar thing. In fact, I'm just gonna copy this command right here. And after we render and before presenting, I'm going to basically transition the image again. Duplicate the code. Okay, and this time it's gonna be probably color attachment here. Let me make sure. Yeah, there you go. So right now we're actually waiting for color attachment right bit. Okay. Oh, hold on, what? Don't you need to do that before ending the command buffer? Actually, yeah. Yep, great catch. Oh my god. Great catch. We gotta do it, of course, in the command buffer because, well, we're recording in the command buffer pretty much. Thank you for letting me know. Okay, there you go. So before ending the command buffer, right? And after ending the rendering, basically. So here, pipeline stage flags, what is that? Pipeline stage flags. It's color attachment output bit, there you go. And for the destination stage mask is basically bottom of pipe. Okay, what else? Now what we're gonna need is, well, image memory barrier. And now we just gotta change the, well, this guy right here. So the old layout, I think the old layout is basically color attachment optimal because, well, we transitioned to it. Yeah, there you go. And the new layout is present SRC, because we want to present to the screen, or to the window. Yeah. Yo, what's happening? Oh, wrong spot. Hold on. Go back. Okay, here. Basically here. Present SRC KHR. Let's go. For the access flags, I think it's bottom of pipe, right? Is it? No, write or read? I think read. Hold on. Where is it? Destination access mask. Yeah, here we don't have destination access mask. Just like when we first transitioned, we didn't have SRC because we're basically ending the whole pipeline at this point, so we don't really need to do that. But we do need the SRC now, the SRC access mask. Okay, image aspect flags. Oh no, access. And here we gotta wait for color attachment to right, I think, isn't it? Yep, there you go. SRC access mask. Let's go. What's next? So bottom of pipe. Where's bottom of pipe? There you go. Cool. So I think pretty much we have done it, I think, at this point. I think that's pretty much it. Let's see. Let's find out. Okay, so there's no validation layers, validation messages. So that seems to be about right. We pretty much have converted our code to dynamic rendering instead of that crazy render pass and frame buffers and whatnot, which honestly didn't make any sense. This make much more sense, and it's much nicer. Anyways, let's see actually what we have changed so far. Great that we have Git. So where can I see all the differences that happened? Okay, here I think. So we pretty much added application info, so we could add the API version here in the instance creation. Then we added a VK physical device dynamic rendering features, dynamic rendering true. We set dynamic rendering to true. And yeah, that's it for that, for the device. Next step, what we have done. Yeah, pretty much we have removed this whole crazy render pass stuff. All this trash is deleted. Next up. And here, instead of passing in the render pass, we just pass in null, but we add a struct into the next field. We push next a pipeline rendering create info into the pipeline creation. And we give it the color attachment format, VK format, BGR8, blah, 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 like the swap chain format, basically. I should probably make that into a variable soon. So yeah, the other one is we don't need frame buffers anymore, so we removed them too. Lovely. And here we go. Now all of that stuff that was in the render pass and stuff like that is actually right here, explicitly defined. So CMD pipeline barrier, CMD begin render pass. So basically dynamic rendering should be the same as render pass. In fact, maybe even better for desktops, and not really for desktops, but basically for immediate GPUs, like immediate architecture GPUs. But for mobile, they use actually tiling GPUs, which if you're using multiple subpasses, then you would probably want to stay with render passes, at least for now. But yeah, that's pretty much the thing. But for our case, it's pretty much the same, or in fact even better, because right now we don't have to like manage all that render passes and frame buffers, creation, recreation, etc., which was very crazy. Also, the synchronization is much more intuitive, much more explicit, and much more coherent with the API. And also, when we get to actually to the engine architecture, it makes it much easier, because right now, instead of having the information about the synchronization in two spots, or even 3 spots: render pass, frame buffers, and command buffer. Right now we pretty much have most of it in the command buffer, and only the pipeline like have the format and stuff like that. So that's pretty much it for dynamic rendering. Lovely. So what we should do next now? Well, let's actually commit this first. Amazing. So this is dynamic rendering. Oops. Let's go. Pretty lovely extension, or pretty lovely feature. Commit. Let's go. So what we should do next? So let me show you a little trick, which is right now we have this triangle, right? Great. Now what if you want to like fill up with geometry, like fill up the whole screen, like full screen, a quad, basically. What we'll do, well, like probably what you would do is like just create multiple triangles, but there's a much nicer solution. But let me show you first the solution of actually creating multiple triangles, so you can see how it works. Let's see. So let's go right. Currently we're not using any buffers, which we're gonna do in a second. But if we go to the vertex shader now, there you go. We're basically just embedding the vertex data into the shader itself at this point, basically. And let me show you how you could actually add more vertices and stuff like that. And now let's actually start by basically putting this triangle in one of the sides. For example, let's say in this place right here, let's make it that way. Okay. So 0.5, well, this vertex right here is basically this one. And for my renderer, I'm using anti-clockwise. So that means that this is the second vertex, this one, I think. Yeah, it is. And this one is the first one, the first vertex. Yep. Minus 0.5 in the X and 0.5 in the Y. Basically negative Y is right here and positive Y is in this section. It's basically inverted from the mathematical background. Okay, cool. So let's see what we could do. So basically this vertex right here, which is basically 0 in the X-axis and minus 0.5 in the Y-axis, I want to actually take it to this position in the screen, which is basically minus 1 in the Y and minus 1 in the X. So let's do that. Minus 1.0 and minus 1.0 here too. Now we don't need to actually compile these because, well, we're compiling at runtime using shader C, a library in our application, so that's lovely. So as you can see right now, we have changed this vertex position to here. Now let's change this vertex to here. How are we gonna do this? Well, this is basically 0.5 minus 0.5, which is basically this vertex right here. So let's actually make it basically 1.0, minus 1.0, and here 1.0. Okay, so as you can see right now, this is correct. Now let's actually take this guy into here, which is basically 1.0 in the x-axis and 1.0 in the y-axis. So 1.0, 1.0 basically here. And let's check it out. And there you go. Right now we got our first triangle. The next step now, we want actually to make a second triangle. So right now what we're doing minus 1.0, 1.0, which is basically this guy, right? So we started from here, and then we're basically going to here and to here. Now let's actually, for example, it doesn't really matter as long as it's anti-clockwise, but let's just go from here up to here and then to here. So basically we're gonna have shared vertices like a shared line, in fact, between these two triangles. So I could basically just duplicate these two vertices that we have here, the first two vertices. The only vertex that would change for the second triangle is basically the third vertex, which is going to be like in the top right corner, which is basically in the x-axis is going to be 1.0, and in the y-axis is going to be minus 1.0. Okay, and I think that's basically it. Did I miss something here? What's happening? Can't assign Vix. Oh yeah, we gotta change this guy. Yeah, we could actually just do this so we can infer it itself. Now let's actually try this out, and I know it's not gonna work as expected. There you go. We still got one triangle. Why? Well, too simply, we didn't draw two triangles. In fact, we didn't even draw 6 vertices. We only draw 3 vertices. Let me show you. Where's the draw command? Where is it? Where is it? Where is it? So begin rendering, bind pipeline, draw. There you go. So here's our draw command. How much vertices we're drawing? 3 vertices. How much instances? 1. How much, what is the first vertex? It's 0. What is the first instance? It's 0. Now, what's gonna happen in your opinion if I change this from 0 to 3? So basically, I'm skipping 3 vertices. Let's find out. Exactly, it will draw the second triangle. There you go. Because since we said that the first vertex would be the index 3, that means instead of starting from 0, it would actually start from the index 3. So it would basically draw only the second triangle. Now, what if we want to draw both? Well, we're gonna start at the first vertex, which is index 0, and then we need to draw 6 vertices because, well, 2 triangles is 6 vertices. So let's draw 6 vertices, or basically, if you want it more readable, 3 times 2, because each triangle have 3 vertices, and we have 2 triangles. And let's check this out. Oh my god, no. Yeah, some calculation is wrong. Hold on. Okay, so what I'm getting wrong here, hold on a second. So what's happening here? Okay, well, so the first vertex is minus 1, 1. So that basically means it's this guy. Oh yeah, the second triangle is supposed to have its space on the top. Exactly, yeah. Let me see what I've done wrong here though. So 1, then here we're going to 1.0. Actually, that's minus 1. Actually, it's 1. Yes, like I'm used to the mathematical version where y is up and y is down. So it's kind of hard to get my mind working with that. Hold on a second. Or honestly, let me show you. This is a good spot to actually show you some trick here to make this even much easier on us. So let's just go back to 3 vertices for now. So I could show you first something real quick. Yeah, let me just show you one thing that we use for shader debugging. Well, in shaders, we don't have print. Well, we do kind of have print, but it's kind of useless in some sense. So let me show you a better way to actually debug in shaders, like on how you will debug your shaders. So right now we have this first triangle that we have right now. Now, how we can actually debug this to know where is the first vertex and where is the second vertex, etc., etc. Well, let's see. So basically, we're gonna do, we're gonna go to the fragment shader. We're gonna create another array, just like here, basically. Just instead of positions, we're gonna have colors. Basically, now colors are basically RGB or RGBA. Let's just go with RGB. So Vic3 colors. You could of course call it whichever you want. And here I could basically like, let's say R is 1 in the first vertex, so basically the first vertex should be red. And then what's going on here? Vic3, yeah, Vic3, and basically gonna have a similar thing here and finally here. So, and basically we're gonna have 0 here, 1 here, 0 here, 1 here. Basically the first vertex is supposed to be green, second vertex, first vertex red, second vertex green, and third vertex blue. Now instead of giving our color a constant value, we could basically give it, well, in fact, notice that this is actually RGBA. It's a vector 4, so there's like the RGB here, but there's also this A. Now instead of this RGB here, we could just say a vec3 right here. Well, actually instead of vec3, we're basically gonna pass in the colors, which is actually a vec3. And of course we're gonna use our vertex index. This is basically a global variable which gives us the vertex index that we're drawing currently, just like what we have done here basically. And yeah, that should hopefully work out. Let's see. And oh my god, let's see what happened here. We have some problem. Let's see. Yeah, we have failed to actually compile the shader. Interesting. Doesn't have, I think, yeah, that's probably the case. That's probably the case. Interesting. Well, we could actually pass it up. So that's probably the case. Yeah, vertex index. So let's actually pass it up, just like what we have done here, kind of. Although it is kind of implicit here for this one. But basically we're going to have something similar to this. But here first in the vertex shader, we're going to have an output. I think this is an int, right? And this is going to be like in, out, hold on, what? Let's just call this vertex index. Okay, and basically what we're gonna say, though, would that even work? Yeah, it would work, right? So vertex index is equal to basically GL vertex index. Basically, we could actually pass values from the vertex shader to the fragment shader, and would basically get interpolated essentially between the fragments or between the vertices, depending on where the fragment is located. You're gonna see how that looks like. So now that we have output, we're basically gonna have the same thing but input here. So instead of output, input, just make sure that the location is the same, which is 0. Actually, that may not work though. Not sure. I mean, this one is 0, so maybe we gotta use 1. But let's see. Let's just see. So now instead of using that, let's use the vertex index and let's see if this works. If it doesn't, you're probably gonna use yeah. Maybe we gotta use another location because probably 0 is used for something else now. Let's actually use 1 and let's try 1. So as you can see, the name doesn't really matter here. The location is what matters. And oh, well, we still have a panic. Interesting. So we have some error. And no, it's because ints need to be float when you pass them. Okay, I see. Well, you got a point there. My bad. So let's actually make this float. And I guess they're not, because they're not floats, they can be interpolated. Exactly, yeah, my bad. My bad. So here what's happening though? Interesting. How are we gonna actually interpolate them? That is another level. Hold on. Colors. Actually, we gotta. Oh yeah, my bad. I gotta actually do the colors here in the vertex shader. Yeah, exactly. In fact, that's the only possible way to do it, really. I just kind of like, I didn't do this for quite some long time now. Anyway, let's just have the colors in the vertex shader, in fact. And basically, we're gonna give it the color, the vertex color. That's basically it. We're basically gonna have something similar here, though the vertex color would be Vic3. Here and here. Make sure to save your shaders. And okay, cool. So now what we gotta basically do here, we just gotta do vertex color that we got from the vertex shader. And here, what we're gonna do basically is, well, colors, GL vertex index. Well, not vertex index now, it's vertex color. Lovely. And let's find out now, I think. I still have a stupid problem. I'm missing out something again. Can I see the message? There you go. Cannot convert parameter 1 from const 3 component vector float to const 2 component. Well, where exactly that is? In 16, in vertex shader 16. You remember that we have actually passed the file name, although we didn't really need it. Well, we actually need it because it would basically show it in the message right here in the debug message. So that's nice. So let's go to vertex shader 16. Okay, so we have some problem here, I guess. Oh yeah, Vic3. Okay. And there you go, we got it, lovely. So as you can see right now, we could actually tell where is the first vertex and where is the second vertex and where is the third vertex. This is the first vertex because, well, it's red, because, well, the first vertex is red. This is the second vertex because it's green. There you go, green. And this is the third vertex, which is blue. There you go, lovely. Pretty easy to see right now which vertex is which. This is how you basically debug in shaders. Basically using colors, essentially, using visuals. And basically, as you can see here, it gets interpolated. Like we pass in the color from the vertex shader to the fragment shader, and it gets interpolated. Now, for example, if we're processing this specific fragment here, or pixel, what happens is that, you know, you get interpolation of that color between this vertex, and this vertex, and you get this specific color in that pixel. And that's how it works. Though you may see that the gradient is kind of off because we're using sRGB. So there's some other thing that we need to do, I think, to make this work correctly with sRGB. Though we could actually, for now, just to see, we could switch up the format of the swap chain real quick. What is it called? sRGB. Okay. So basically, instead of BGR8 sRGB, let's go with UNorm, I think. Yeah, it's probably UNorm, right? I don't know, maybe we're gonna need to actually change some things too. But... oops. What's happening here? Vertex count 3. Go to sRGB. Okay, replace this. I gotta actually make it honestly into a variable. sRGB nonlinear. Yeah, honestly, let's do it right now. Let's do it right now. So this guy right here, we gotta replace it with basically a format. Swap chain format, and replace. So basically we have the format, we have mentioned it in the swap chain itself, of course, and we have mentioned it in the pipeline and in the, what is this, swap chain image views. Okay, so let's actually replace all with swap chain format variable, and let's just create a variable now. I should have done this very too long time ago. But anyways, so let's just have a swap chain format here. Doesn't ID have a functionality to extract out a value into variable? Probably, but I'm just old school, I guess. So let's swap chain formats is equal to, but I actually should try to learn my IDE really. And hold on, I'm gonna be back just in a second, real quick. Coming back in a sec. Okay, so I'm back. I just changed up because I wasn't comfortable in that clothing very much. So let's actually go with vk format BTR8 SRG. So this is what we had before basically. This should be exactly the same, just right now we're actually controlling the format in one variable instead of 3 places. Now we could actually try the different formats. For example, norm. Let's see. Well, of course, your GPU and your system should be able to actually handle this. But there you go. This is what we actually get for unorm. Blue, red, green. You could see that it's different, pretty much. And we actually have to handle such difference later on. Though for now it seems fine. Looks darker but more saturated. Exactly. Though maybe I could look for how to actually fix it now. I don't really remember exactly how you do it. sRGB fix, I guess. So pretty much I think we gotta do some gamma correction. I still don't understand exactly how that works, but let's see if we can find out something here. Right, do set propensity lighting in linear space, then apply gamma correction. And this is actually fragment color. Yeah, let's try this out. And see if that would help. Because monitors display colors with gamma applied whenever you draw, edit, or paint a picture on your computer, you're picking colors based on what you see on the monitor. This effectively means all the pictures you create or edit are not in linear space, but in sRGB space. Doubling the dark red color on your screen based on your perceived brightness does not equal double the red component. So it's basically about, well, color perception in our eyes, essentially, with monitors. So without gamma correction, there you go, it looks darker. But with gamma correction, it looks much lighter, which is what's supposed to be the default, basically. We have to make sure texture artist works in linear space, since it's easier to work on. Most tools don't even properly support linear texture, and this is probably to recorrect or transform these RGB texture to linear space before doing any calculation. You can do this as follows. Okay, so I think what I need is basically this. So first, let's grab the gamma, which basically is set to some value, probably depending on the monitor, pretty much. So vertex shader fragment, yeah, we need it here basically. And let's just say gamma. Though maybe actually it's better to do it probably in the vertex shader. You know why? Because, well, instead of doing that gamma correction, I think maybe in like in the fragment shader for every single fragment. We could like do it in the vertex shader, which basically we're gonna do the calculation just 3 times, like for every vertex. So let's try that first, and let's see actually if that makes a difference. I mean, it depends, because well, we still have interpolation, so I'm not sure about that. Let's see. Let's find out. So here we just need the power here, and basically do something like this, and this color is right here. So basically power of 1 divided by gamma. Let's find out if this is actually right. Okay, well, what we're using right now, hold on. We're using sRGB or what? Yeah, we're using sRGB, lovely. Cool. So I think right now it looks more natural, isn't it? Not sure. I guess let's find out. And how are we gonna find out? Well, I can't tell. Me too. Let's see 1.0 again, I think. Yeah, I really can't tell too. So bad at colors. Well, here's what we could do. We could basically just take a screenshot, essentially. So this is the color with the gamma correction, whichever that is. And now let's actually check the color by itself. Okay. Oh my god, where's the screenshot that I took? Damn. It just gone. Weird. Well, let's take this out. Okay, there you go. So right now I took this one. Okay. So now let's actually remove this and remove the comments from here. Let's find out. I don't know. Maybe I'm not supposed to actually do it in the vertex shader. Probably I'm supposed to do it in the fragment shader, maybe. Maybe that's why. Though I can't really notice any difference. So yeah, let's try to do it in the fragment shader instead and see what's gonna happen. Okay, cool. Let's do that. Well, now let's basically go back here to what we had before. Let's remove this. Well, actually, let me grab it. And let's remove this. Okay. Now let's go back to the fragment shader here. And instead of vertex color, we're gonna do this. And instead of this, we're gonna do this. And the gamma, let's say 2.2. Oh my god, no. That doesn't seem good. That seems much lighter than it's supposed to be. Yeah. What if it's U-norm, by the way? Maybe this is actually the inverse of what we want. Okay, that looks very bright. Yep. Yeah, I think this is probably the actual solution for U-norm, when you're using U-norm and then you want to make it like sRGB or something like that. Anyway, so yeah, I think this looks more natural. So basically this is not the exact format that I want. Basically I think I want the inverse of this. So let me see. So we have used this one. Probably we gotta use maybe this one or something. I honestly not sure. I gotta get back to this later on. But anyway, but I think this works for now. Maybe. Well, let's just leave it as it is for now until later on, until I research more about that. Okay. Well, go back to what we had before. There you go. And here, same thing. In fact, we're still good here. Okay, cool. So let's just remove this for now. Let's just keep it as sRGB. Later on, I'll check it out, see how to do exactly right. But anyway, or maybe it's actually right already, but IDK. Anyways, never mind. So now let's just go back to the two triangle stuff. So what we have done, basically we were, okay, let's see which vertices we need. Basically we need this vertex, which is the blue vertex, and the green vertex, the blue and the green. So that means the blue and the green, which means this guys, not these guys which I was using before, these two, blue and green. So let's actually use these. Let's use those. So how are we gonna do with that? Well, we're gonna basically say, yeah, we're gonna basically duplicate these two. Or is it? Hold on, what? Yep, pretty much. We're gonna duplicate these. And let's go. And finally, we're gonna make our own new vertex right now of that triangle. And that one would be in the top right, which is positive x and negative y, right? So let's go ahead, see. Oops, yeah, we still haven't right now does that, but before that, in fact, let me just make sure to actually do the same here in the colors, otherwise we're gonna get a nasty error, I guess, or something like that. Basically, we're gonna have a buffer overflow or array overflow, or yeah. So let's actually go to where we're drawing the vertices. Where, come on, I need the train. There you go, 6 vertices. And let's find out now if this would work. Come on, what? How? Did I actually not did it right maybe? So yeah, I think so. Basically I've done green, blue, and here, green, blue. Yeah, which is clockwise. Well, we don't want that. We want anti-clockwise. In fact, so we gotta basically do, just invert these. The last should be the first, and the first should be the last. Basically flip them, their positions, and there we go. Though this is kind of wrong. So anti-clockwise. So it's basically going like this, right? So instead of green, I want blue. So instead of green, which is this, I want blue. And this should look, I guess, correct. And there you go. We got a quad on the screen, which is awesome. Though, of course, you cannot resize that. Yeah, at least not yet. Okay, there you go. So we got a quad on the screen, full screen quad. But the problem with this, though, is that this is not the most optimal way to do this, like to do a full screen quad. Because, well, here we have 2 triangles, right? So, well, first of all, we have 2 triangles, pretty much, instead of 1. And also we have some overdraw here. Like, basically, these 2 share this line. So there's a lot of overdraw. Basically, some drawing that we doesn't really need to do. So here's a little trick. Let me actually show you, first of all, an image in Google, basically. Let me first of all see where I can find that. Full screen quad, or actually full screen triangle. And let me show you the image. There you go. Okay, so here's an example, basically. So what we could do, we could use only one triangle, in fact. We could use one triangle to fill the whole screen, and then we could basically correct the UV. So, and here's a good article about this, by the way, if you want to check it out, which is pretty cool. I have a lot of information there, and yeah. So basically, the GPU actually processes the like 2x2 pixels. Well, it can change, of course, from GPU to GPU, but this is just generic, like simplified. But there you go. And of course, there's overdraw here between the edges of the two triangles. And of course, we're actually using two triangles instead of just one. So let's actually try this out just as a little exercise. So instead of two triangles, we only need one triangle. Only one triangle now. Amazing. And let's try that out. So now only 3 vertices. So now we're pretty much back into the first one triangle thing. There you go. One triangle. Now basically what we're going to do, we're going to scale this so it fills the whole screen. And of course there's a lot of ways you could do this. But I think a pretty intuitive way is to just scale the vertices up 3 times. Because well, the screen actually, the screen size is like 2, not 1. It's 2, because it doesn't go from minus 0.5 to 0.5. It actually goes from -1 to 1. And then of course we need the margin to actually fill the whole screen, so it would become 3. But anyways, let's see. Positions, which vertices right now I gotta change? I gotta change the green and the blue vertex. So the green and the blue, which is basically this and this. So this would basically become 3, 3, 3, 3. Or we could just say multiply by 3. Oops, no. What? Hold on, really? That doesn't make sense, does it? Why change the color instead of the vertex? What? I'm confused. So this is positions. Okay, what happens if I like do ×2 now? And what is happening? Somehow weird. Position GL vertex index. And that should be correct. Like, why it changes the color? Weird. Colors. That is another level. Very weird. Why? So that's 0.5, that works. But like basically when you scale it up, it doesn't. Oh, actually, hold on. I'm doing it actually wrong, first of all. Oh, yeah, my bad. I see what's happening here. Well, so this guy right here, which is like 1, 1, which is essentially in 1, 1 down here. So this would need to basically be just in the x-axis, and this one should be in the y-axis. My bad. And there you go. Right now we got one triangle for a full screen quad, but you could tell that the gradient is off. It's not as it was before with 2 triangles, because well, we gotta correct the UV. We gotta correct the UV, and how we can do it? Well, Let's basically go to GL position, vertex color. Okay, in the fragment shader, let's actually fix the UV here. So, but how I do? I'm gonna do it. Hold on. We don't even have the UV, is it? No, we do not. Interesting. Well, we gotta actually pass in the UV, I think, first of all. Yeah, I think we gotta pass in the UV. By the way, hold on a second. Would 0 work here? Real quick. Yeah, that actually works just fine. Okay. Okay, let's actually create another variable that we could pass to the fragment shader right now, which is gonna be 1. And here, let's call this vertex UV, I think. And let's just pass this up. Vertex UV is essentially will be equal to this guy right here, the positions. Oops, keep that one. And let's just say vertex UV is equal to that too. I guess that's it. Though, of course, this should be Vic2. And right now, I'm just going to copy this guy, paste it here, and then input. And here, we're basically can, well, we got the UV right now, which is nice. Okay, well, how are we going to actually do it? Interesting. I'm honestly not sure really how that would work. Well, like we do not have a texture, we actually have vertex colors, which is interesting. Not sure how that would work exactly. But let me, I guess, just see what's going on here maybe. Like if I say vertex UV, what's gonna happen there? Cannot resolve constructor. Actually, by the way, instead of passing in the color, I could have just passed the UV. Cannot resolve constructor, Vic4, Vic2, float, 3 elements found. Cannot resolve. Oh yeah. So, well, this only gives us that, okay. So let's actually add another component there, which is gonna be 0.0. Okay, so this is the UV basically. So like the X is red and the Y is green. So like, and in fact this is negative, like that's why it's black. So I actually gotta fix that first. So basically I gotta times 0.5 plus 0.5. So I could fix the range. And there you go. Right now we're actually getting the proper UV, which is getting from going from 0 to 1 and from 0 to 1. Cool. So now that we got the UV, how we could actually do it? I mean, yeah, we don't really even need those colors anymore, really, anyways. So there you go. We got the UV. Cool. In fact, instead of doing this guy here, in fact, let's pass in the UV proper from the start, in fact. And we don't even need the vertex colors anymore, really. Who cares? Let's remove the colors. And we could just keep the UV. Location 0. And here, we're just gonna do that transformation here so we can normalize the UV. Basically, I think. Is it? Actually, what? I don't think that works, is it? Hold on. Having some problem here. Oh, I see. This should probably be Vic2. Maybe. Well, not really. Hold on. Go back. What is the actual error? Undeclared identifier, vertex color. Yeah, we don't need this. Okay, so yeah, X, Y. Is that correct? Well, not really, honestly. Because, well, we got some vertices that aren't really normalized. Like here, it's actually 3. But we could normalize them. Maybe. Well, anyway, never mind. This really doesn't even matter. Anyway, let's just go back right now to what we had before. So I just wanted to show this one. Now let's just go back to Vulkan stuff. Okay. Okay, great. Let's remove these. We don't need them. And here we don't even need these. And we don't need this stuff right here. And for the fragment shader, we don't need this stuff. And we could just keep this as 1.0, comma 1.0 for now. Or actually 0 or 1.0, white basically, white color. And yeah, we're back into what we had before. Though, let me make sure that I'm basically drawing only 3 vertices, so that's nice. Okay, so that's pretty much it for that one. Now let me actually make sure to use synchronization too, I think. Let's see. Synchronization 2. By the way, this is the link of the other one too. There you go. Okay. Now let's go back to Vulkan. This extension modifies the original core synchronization APIs, simplify the interface, improve usability of these APIs. The 64-bit range. Okay, as we have run out within the 32-bit range, the new flags are identical to the old values within the 32-bit range. Without sacrificing precision. Ambiguous specific accesses in a given stage or set of stages. Basically, this extension would give us more precision over and more coherent API towards synchronization. So we could have like more optimal synchronization essentially. So yeah, light transitions would be simplified as well. There are generic attachment. Oh, okay, so these are the generic ones that we've seen, and layouts which are contextually applied based on the image format. All right, I see. So right now, instead of telling it like layout color attachment optimal, we only need to tell it layout attachment optimal, and then it's basically going to infer from its format, like is it color or depth or what exactly. Yeah, I see. We actually used it here. Well, in fact, we didn't use it here, is it? Yeah, we didn't. So let's actually try to use it. Image layout attachment optimal. So instead of color, we could just pass in attachment optimal instead. Can I just say attachment right too? No, not that one. At least I guess so. Unless if there's like an access flags too or something. Yeah, I mean there is, seems like. No. I mean there is too, but it's not what we're but yeah, let's actually use access flags too, why not? It's basically drop-in replacements, I think, but it probably adds like more stuff essentially. So we're just gonna replace access flags with access flags 2. I'll replace all, I guess. What? Expected access flags? Weird. Hold on. VK access flags. But why? It didn't work out. Oh, this guy is expecting, I see. So basically if I do this here, it wouldn't work because, well, it is actually expecting it to be access flags 1. Yep, I see. So let's actually go step by step. Hold on. First of all, I think we don't need color attachment optimal anymore. Well, is there like color attachment output? No, of course not. So what we have actually changed, hold on. So VK image layout, attachment optimal, and read only optimal. I don't think we have that, which are contextually applied. Okay, replaces also functionally replaces VK image layout shader read only optimal. So okay, cool. Events are now more efficient because they include memory dependency information when set them on the device. Previously, this information was only known when waiting on an event. So dependencies could not be satisfied until the wait occurred. That sometimes meant stalling the pipeline. When the wait occurred, the new API provides enough information for implementation to satisfy these dependencies in parallel with our tasks. Queue submission has been changed to wrap command buffers and semaphores and extensible structures. From Vulkan 1.1. Okay, extensible structures. Okay, see, VKHR device group and VKHR. Okay, we also got timeline semaphore and device group. We don't need this, but we do need this. This is very, very useful. This also adds a pipeline stage to the semaphore signal operation memory in the existing pipeline stage specification for wait operations. As interaction only with the device, allowing more efficient access to the inline objects. Oh yeah. Now, in fact, with timeline semaphore, we don't even need fences anymore. Well, only for one thing currently, unfortunately, which is interacting with the Windows system, like WSI, like basically the swap chain, essentially. So that one expects a binary fence, I think. So that's the only place where fence would still be used. But other than that, nope. So yeah. Yep. Queue submission has been changed. Okay. The not preferred image layout can be specified by setting equal to new layout. Huh? Image memory barriers that do not perform an image layout transition can be specified by setting all layouts equal to new layouts. Like, that wasn't the case before, or what? I mean, example, the old and new layouts can both be set to VK and defined without discarding data in the image. Oh, I think maybe before that wasn't the case. That's crazy. Queue family ownership transfer parameters are simplified in some cases. Queue family ownership transfer. Interesting. Where two synchronization commands need to be mashed up. Queue events. This information. Extensions with commands functions. Siege flags 2KHR. The new events and body interface are now extensible for feature changes. Let's go. Relevant pipeline stages mask can now be specified as an empty with the new VK pipeline stage non-KHR and stage 2 non-KHR. Can be changed to subpass dependency. We don't need that to write in the original. And yeah, they also start using 64-bit instead of 32-bit because apparently they have run out of 32-bit stuff. Okay, 32-bit flags. New base type, VK flag 64, and all this cool stuff right here. Pipeline barrier 2, so let's use that. Queue submit 2, what we're using to, well, yeah, pretty much this is the only ones that I need to change, like pipeline barrier and submit to the new ones. Okay, let's see. So I guess let's start from the top to the bottom, I think. So where we have synchronization. So in-flight fence. I mean, hold on. Can I actually use timeline semaphore here? Hold on. Where I'm using this, first of all. I'm using it in QSubmit, which there is QSubmit too. And wait for fences. I mean, probably. Let's just see. Let's go step by step for now. Okay. Acquire next image. Begin command buffer. Now this one, yeah. Okay, so this one would change to pipeline barrier 2. Let's actually change it to that. I wonder if I have to like maybe enable some feature. Maybe that's the case for like, I guess, timeline semaphores. I don't know. We'll see. I mean, let me check. I mean, we have a new struct that we have done for dynamic rendering too. We could maybe check that out. There you go. So this is all the other features that we could actually enable. Oh, there's only one. Oh, interesting. Yeah, this is all dynamic rendering features. Oh well, okay. Well, anyway, never mind. Let's go back to pipeline barrier. There you go. Okay, so now let's basically use that guy instead. So device.command. Now instead of pipeline barrier 1, we're going to use 2. And here we need, of course, to give it the command buffer just like before. And now instead of all this crazy arguments right here, which was nasty, we're gonna give it like a struct, just like how Vulkan actually works normally. I don't know how they missed this one, but there you go, they fixed it. It's more coherent with the API now. Lovely. Okay, so dependency info. There you go. And now what we could actually give it, we could give it all this stuff. Dependency flags, image memory barriers. Lovely. So what we need right now is image memory barrier. From ref, image memory barrier 2. Okay, cool. So vk, well, reference of course, image memory barrier builder, and let's check this out. So we got sub-resource range, we got src access mask, destination. It's pretty much, I think, pretty much the same, kinda. Let's actually try this out. I mean, for example, let's just give it the sub-resource range, and this is probably the same kind of. Let me see. By the way, what this is dependency info but found builder. Oh, let's give this C reference, and here let's try this. Oopsies. Well, that makes sense. But well, let's just do this, and let's just copy this stuff. I think should be kind of similar, but this one will be 2, I think. There you go. What else? Yeah, I think that's pretty much it. Color attachment optimal. I think this one could be just attachment optimal instead. I don't think this could be attachment right. No, you need to give it what exactly. Cool, lovely. What else? Aspect mask, color. Yeah, that seems about the same thing. Okay, now we gave it the image memory barrier. What's next? Now we need to probably give it the other stuff, which is like, where's the src stage mask, for example? Oops. Where they are? Maybe dependency flags? No idea. Buffer memory barriers. Yep, probably dependency flags. What's this? Oh, no, that's not the case. But how do you actually set up the other stuff? Interesting. Like, where these things have gone. Crazy. Okay, let's go to this one. Let's check it out. Call this. It takes dependency info. Okay, this is it. So we have given the image memory barrier. Yeah, that's pretty much it, or the equivalent. Maybe it's actually right now, maybe it's inside of image memory barrier itself actually. Hold on. If I say dot, there you go. I think so. Not really. No. Very weird. But anyway, let's see what's gonna happen right now, honestly. So let's just remove the old one. Did we already remove it or what? Oh. Oh, I was actually dealing with the wrong one. Hold on. So I meant okay, I meant this. And where is, well, not this, but this. Okay, stage mask. Interesting. I think this is probably it, right? Yeah. Pipeline stage flags too. And it was color attachment optimal. No, the top of pipe basically, because well, we're just starting out in the pipe, and then color attachment output. Yeah, pretty much. So now basically instead of having these as arguments, right now we have a struct, and instead of having these pipeline stage mask stuff for all of the barriers, right now we have it like local to each one. Like for image memory barrier by itself, like for every image memory barrier you have to give it the source stage mask, and that's much nicer, much more intuitive, honestly. So right now we could probably just comment this out. Pretty lovely. Love it. Okay. Destination stage mask. And this would be vacate pipeline stage flask 2. And now I could basically see color attachment output. Now this should be the exact same thing. And maybe it's a drop in replacement, so I could basically change one after the other, upgrade one after the other. And yeah, that seems about right. But there's some validation errors. Interesting. So let's see what are those validation errors. Synchronization 2. Oh yeah, synchronization 2 feature is not enabled. The Vulkan spec states synchronization 2 must be enabled. Interesting. Let's go to, oh my god, it's gonna, yeah, this is gonna take years to reload. Okay, hold on, let me show you a better one. Vulkan spec 1.3. No, not this one. There's a page where you could actually, like, it's called chunked, I think. Yeah, probably chunked. Yeah, there you go. And basically here in Vulkan 1.3 API specification, instead of this single file HTML or PDF, which takes very long time to load, especially the single file HTML, I'd like to go with basically chunked HTML. Now, yeah, let's go with this one for all published extensions, I think. Or we could just go with the core API. Yeah, let's just go with core API for now. Chunked HTML. Now, in fact, I could go step by step to where I want without without waiting for it to load everything up, which takes years. So we're looking for synchronization too. Okay. Hold on, where is the... Weird. Where exactly that is? It's in Vk. Oh, let's check for VK-CMD pipeline barrier. There you go, pipeline barrier 2. And then we could hopefully go from there to the feature synchronization scope. Okay, synchronization to feature. Feature. There you go, synchronization 2. I think it supports the... Weird. Okay, go back to the actual thing here. Well, where is it? Hold on. Synchronization. There you go, I think. No. Synchronization 2 extension. There you go, this one. And let me just see what they added, and we can probably find it there maybe. It's basically extending VK physical device features too. Lovely. With VK physical device synchronization 2 features KHR. Interesting. VK physical device features 2. Okay, let's check that out. VK physical device. Come on. Is it like here maybe? VK physical device features 2. Let's check this out. That can be supported by an implementation. It's defined as this or the equivalent. Defined by extensions, can be used or can be included in bean exchange. Okay, VK device create infrastructure, which features are enabled on the device. Lovely. Okay, so basically the same thing that we have done with dynamic rendering, but basically here push next and mutable VK VK physical device 2 features 2. There you go. Builder dot features. Hold on. Features. There you go. And here, what we gotta do? VK physical device. Features, I guess. Builder. Okay, and then here we gotta give it a reference. Cool. But what's happening here? It's expected. Oh yeah, actually I need to build this. Okay. All right, now I could probably include that. Now, there you go. This is all the stuff that I could actually enable here. Like multi-viewport, shader float 64 if you want that. Wide lines, let's go. Interesting. Vertex pipeline stuff, nice. Let's go right now with synchronization 2, hopefully. What? Oh, interesting. Well, maybe I gotta push it. That's weird. vacay physical device features. Oh, this is should be 2. Oh, well, basically, we don't really want these features. We want actually to push another one, which is gonna be like mutable. And yeah, we gotta actually push right now this guy right here. This synchronization features. Okay, so this is called vacay physical device. Synchronization 2 features filter. And right now here I could say synchronization 2 true. Okay. Oops. Something is totally wrong here. Push next. What? I'm confused. Okay, there you go. But what's happening here? Okay, there you go. Let's go. So right now, as you can see, we have enabled synchronization 2. Now that shouldn't be a problem anymore. There you go. We don't get that validation error anymore, which is nice. And in fact, I think it only got one. Yeah, you got only one field. Like you need the whole struct just to include that field. Interesting. Well, yeah. Okay. So what's next now? Yeah, let's actually get on upgrading the other ones now. Nice. So as you can see, it's drop-in replacement, so you could like upgrade incrementally one by one instead of having to upgrade everything at once, which is very cool. Okay, so right now we basically have upgraded this one, so we don't need this anymore. Much cleaner, honestly. Love it. Now, yeah, basically similar thing here. And also I'm just gonna copy this guy instead. This MD pipeline barrier 2 here, essentially. We could probably even put it into its own like its own function, honestly. Because we're gonna be doing this a lot probably. It's like basically image layout, new layout, and also the access masks also changes. Other than that, not hardly anything else. Also maybe the aspect mask here. And yeah, and also the source stage mask and the destination stage mask. I think so. But for now, let's just keep it, you know, top down. No need for functions, so it's friendly for beginners, I guess. But well, we'll see. We'll see. Anyways, let's just for now. Let's just do this without any crazy abstractions or functions or whatever. It also helps me like not go crazy about abstraction, because once you start you just never end. Okay, it's actually quite, it's like in Rust it's not as easy as just abstracting some code block into some function. It's like you go in a crazy it's like the memory checker would just make it hard sometimes. Anyways, so right now what we need color attachment, output bit, and top of bottom of pipe. Well, so essentially image, yeah, and then the old layout. The old layout would be attachment optional. The new layout would be src represents src essentially. And the destination access mask is probably nothing. Right now I think we need maybe, hold on, maybe we need here src, right? src access mask, yeah, src access mask, and we need color attachment, right? Nice. And we also need, this stays the same of course, And here this changes. This probably is bottom of pipe, I think. And this one is color attachment output. There you go, bottom of pipe. Makes sense. Makes total sense. Love it. Okay, cool. I think that's pretty much it. So now we could hopefully remove that, but let's check out this first. Lovely. Love it. So right now we have upgraded that function too, which is amazing. Okay, what's next? So also we have right now queue submit. Let's upgrade that too. Cool. And then later on, maybe we'd like to try to see if a timeline semaphore can actually like take the place of this fence. Hopefully, we'll see. Yeah, maybe. We'll see. Okay, so queue submit. Queue submit. Well, we have queue present and queue submit. I think both would be needed to actually upgrade it. No. Actually, no. Queue present, we cannot really upgrade it though. I think, yeah. I mean, it's part of another extension, pretty much. I don't think. Yeah, pretty much no. But there is a QR next image too. Only available since Vulkan 1.1. Interesting. So that is something that we could also upgrade. Why not? Okay. Let's start with queue submit here. Let me make sure I didn't mess up anything while I was playing here. I'd like to always test up before I do some new changes. Okay, so here we go. So now end command buffer, queue submit. Okay, so let's actually, yeah, let's use queue submit 2 now. Queue submit 2. Now here you give it the queue as before, and then you give it submit info. Now this time it's submit info 2 instead, and you still give it a fence. Ooh, why a fence? Well, I think you could probably still, oh, okay, hold on, never mind. Let's just see what's gonna happen there. Wiki submit info 2. Builder. Cool. And what's next? So we gotta need, of course, wait semaphores, right? But let me see like what is new here, or what is changed. There's flags, signal, semaphore, infos. Oh, now it's, instead of a slice, it's actually a struct, I think. Maybe. Interesting. So let's go with the wait semaphores now. Infos. And this requires a semaphore submit info. So yeah, a struct. A slice of structs instead of slice of semaphores. That's pretty cool. From ref. I guess I see where this is going. Semaphore submit info. I'm so excited. And of course, let's add the semicolon there so we could see the format. Right. Probably need a reference here. Maybe. And of course, we gotta unwrap this. Okay, cool. Takes 3 arguments. Q 3 arguments, okay. Defense. For now, let's just give it none and let's see what's gonna happen, really. Or let's just give it in-flight fence until we see what happens with the other stuff. Okay, cool. Now, this is from ref, and of course here we need reference. So we could build it, and then let's see what we have here. Okay, we have some other crazy stuff now. So we could basically pass it a semaphore. Now, how can I actually pass a timeline semaphore? It doesn't really give that. Weird. Semaphore submit info. Let's check this out. I think, yeah. Let's check this out. hold on. There you go. So S type KP next semaphore is a vacay semaphore affected by this operation. The binary semaphore value is either the value used to signal semaphore or the value weighted on by semaphore. Oh, the value. So this is actually preparing for a timeline semaphore. Okay, I think I know where this is going. If semaphore is a timeline semaphore, otherwise it is ignored. Okay. I see what's happening here. Stage mask is a vacate pipeline stage flags to mask of pipeline stages, which limit the first synchronization scope of a semaphore signal operation, or second synchronization scope of semaphore wait operation is described in the semaphore wait operation and semaphore signal operation sections of the synchronization chapter. Crazy stuff. The device index is the index of the device within a device group that executes the semaphore wait or signal operation. Of course, this is useless for us here. I'm not sure about this one. Maybe this basically gives like more precise control over the synchronization. And this one basically for timeline semaphores, which I may want to use. Alright, pretty cool. But for now, let's just upgrade stuff step by step, honestly, instead of going all in. If the geometry shader feature is not enabled, stage mask must not contain stage 2 geometry shader bit. Makes sense. Okay, anyway. Alright, lovely. Let's go back now and builder dot semaphore. Right now I'm just gonna basically upgrade step by step, and let's just give it the semaphore that it's expecting, which is in this case wait semaphore is image available. There you go, much cleaner. What else? Now the signal semaphore, right? So wait semaphore. Semaphore infos. Now basically need from ref. Vacay semaphore submit info. Builder. Dot. Okay, here we gotta give it the render finished semaphore. The signal. And let's go. Actually need to give you a reference. Cool. Lovely. Okay, what else? Command buffers. Still haven't gave the command buffers. Command buffer infos. Oh, instead of command buffers right now, we also have command buffer submit info. Crazy stuff. Yeah, I see. But honestly, structs rule them all. Basically, so that's nice. Okay, submit info basically allows you for greater control. Command buffer. Currently, it's only have device mask and yeah, which is relevant for us. I think command buffer, which we could just give the command buffer to. Okay. And I think maybe that's it. There's still this wait DST stage mask. Interesting. I think maybe I know what this is going. Oh, okay. So now instead of having again that wait DST stage mask for everything, for the whole command, we have it for each and every specific semaphore, basically, seems like. Yeah, that's essentially it. Nice, lovely. So here, this wait DST stage masks would go into the wait semaphore infos. So semaphore dot stage mask, maybe. There you go. And right now we could actually pass in this guy. Attachment output. pipeline flags too, of course. Though maybe we don't need color anymore. Maybe attachment output. Actually we do. Yeah, we do. Okay, cool. So basically we give this sage mask here. Now, interestingly, I think, do we even have a weight SRC mask? Hold on. Yeah, we don't have a SRC. Well, if I'm correct, if I understand this right, then now, instead of just for the wait operation, actually not wait, I mean, sorry, signal sage mask. Yeah, we don't have a signal sage mask. Do we even need that, in fact? I mean, let's see what we have here. Yeah, there's in fact here a stage mask. So right now we could even control the signaling. Very interesting. Well, let's see what's gonna happen just with this, step by step. So now queue submit, we have this queue submit too. It's basically almost one-to-one mapping for now, but we still have a lot to actually upgrade basically. Okay, so the first thing that I see is that we could actually give it a signal stage mask. I'm not sure what that would be useful for, but I mean, it basically gives us more control, but how? Let's see. So semaphore, okay. So signaling. Now who's waiting for this signal? The render finished semaphore. This guy. And this guy. Okay, let me see the pipeline flags that we could actually give. Top of pipe, bottom pipe, blah blah blah. Color attachment output, of course not. Bottom of pipe, maybe. Top of pipe, nope. Clear, none. That's also something possible, which is basically the default one. And if we're gonna do that, then you'd better just remove it altogether anyways. Okay. Copy all commands, no, I guess. All transfer, oh well, that's something. Blit, bottom of pipe, color attachment output, computer shader. Can I see transfer stuff? All transfer, KHR, all transfer. Okay. There's transfer and there's transfer feedback and all transfer. I mean, I guess I could say transfer here. I don't know what I'm doing exactly. But let's see. I mean, it doesn't. An assigned status message. No, this is just a message. Okay. For dependency, ash includes semver metadata, which will be ignored. Removing the metadata is recommended to avoid confusion. Interesting. I guess maybe let's remove this thing right here. Yeah, makes sense. And also, I don't need the info. It's just annoying. Well, let's hope that's correct. But yeah, it seems fine for now. Hopefully that wouldn't ruin me later on. But there you go. Right now we have one extra knob with the queue submit. In fact, a lot of other nodes, but there you go. Now, can I actually, instead of in-flight fence, basically create a timeline semaphore and then use that essentially? I think. But we're gonna come back to this later on, I think. Why not? Okay. Now, what else? Queue present. Of course, I cannot really change that. But I remember there was some other one here in... where is it? Where is that guy? There you go. Acquire next image. So can I use acquire next image too? I'm not sure like what's new there, but let's see. Swap chain extension dot acquire next image 2 on success unavailable. So this is available since Vulkan 1.1. So that's interesting. Or isn't that the exact same? No. Oh, I see. So this is right now a struct instead of arguments again, which is much nicer again. It's much more coherent with the API. And I think maybe only info. EKHR and builder dot. So there is swap chain, of course. I wonder if it's just one mapping, or, and then there's like semaphore, fence, device mask. Okay, so there's device mask. Yeah, that's the only thing that got added, and of course it got changed to struct. So now it probably be or is able to like be extended using pnex. So that's lovely. Okay, swap chain, and we also need. Well, let's set the timer to 64 max. And also set the, well, fence, I'm just gonna keep it as null. And then the semaphore to image available semaphore. And there you go. Nice. And of course this actually could fail just like the one before. And there you go. Now what this returns again? I guess the same maybe. Let's figure it out. Is it the same? Yeah, pretty much the same thing. Nice. And I think this should be enough now. We have some validation error now. Device mask must not be 0. What? What do you mean by device mask, by the way? Interesting. Maybe you actually really need to give a device mask in this case. I don't know what exactly it is. It's a user 2 though. So maybe you're only supposed to use this acquire next image 2 version if you're using like multiple devices, I guess. Hold on, what they said about it. It's been created image whose is returned. Okay, forward progress cannot be guaranteed. Blah blah blah. No. Let's go here. And device mask. It's a mask of physical devices, for which the swap chain image will be ready to use when the semaphore fence is signaled. Weird. If acquire next image KHR is used, the device mask is considered to include all physical devices in the logical device. I think I see what I'm supposed to do. Signals at most to one semaphore, even if the application requests waiting for multiple physical devices to be ready via the device mask. Can wait on that semaphore. Okay, so this is basically vk acquire next image KHR with device mask being, I would guess like U32 max, I guess. Well, not really max, but basically it should be like the binary should be 1111. So can I do this? Yeah, so basically full, like all bits on, hopefully. Let's see. Physical device is 1. The Vulkan spec states must be a valid device. Oh, well, not really. So physical device count is 1. So maybe it's expecting 1, I would guess. Otherwise, I would expect 2 or 3, depends on the access mask. Okay, so 1, basically because we have only one device. And I wonder about the other ones that have device access mask. Like, is that like not needed? Or what exactly is going on there? Weird. Okay, where is the device access mask again here? For example, maybe this one. No. Okay. Let's check out the new stuff. Like, for example, let's see if this will have it. Not really. Okay, what about this guy right here? No. This guy? No, of course not. I don't know where I've seen it. Again, seen it somewhere else. Yeah, I think here. Yeah, it's calling it device index. Interesting. Well, that's not what I expected. Okay, can you give me the link to the documentation of this guy instead? Or let's just say semaphore submit info. VK semaphore submit info. Let's go. And device index is the index of device within device group that executes the semaphore wait or signal. Okay, so this is the device index, not a device. What is it called again? Not a device mask, basically. Yeah, so it's fine to be 0 essentially. So okay, cool, lovely. So now that's it for that one. What else we could actually upgrade? Let's see all the functions. Begin. There's only render pass 2, which we don't use anymore. Goodbye to render passes already. Okay, begin rendering. Bind pipeline. Bind. Nah, of course not. Begin. No. Okay, so everything is good now. Yep, pretty much everything is good. Lovely. Pretty much have upgraded to that. I don't think we have QPresent 2. I think I've already checked that. Unfortunately. So yeah. Which means that this render finish semaphore, for example, cannot be. Well, maybe it can. I don't know. No, it's probably cannot really. Yeah, this only takes binary semaphores, pretty much, not timeline. Wait for fences. Reset fences. Okay, interesting. So now let me actually add. I think this is probably the last one that I'm gonna do here, which is essentially try to. Okay. By the way, before that, can I remove this reset command pool and just add a flag? I think, hold on. If we go, well, no, yeah, I do remember right now what I've done there. Yeah, no. Okay, what else? Yeah, let's actually try right now to make, instead of using an in-flight fence, maybe let's try to use in-flight semaphore. I'm not sure how exactly that would work, but let's see. like no idea. Like, how do you even create timelines before? No idea. Oops. Okay, let's check out how to create a timeline semaphore. Vulkan timeline semaphore. Okay, do it here, I guess. Semaphore type. So maybe here. What do you mean by type ID? No. Oh, not here. Hold on. Builder. What? Type ID. No type here though. Make a semaphore type. Create O. Okay. And then here make a semaphore create info. Which is timeline create info. Oh, it's in the P next. Interesting. Makes sense. So P next, you give it the timeline create info. Okay, lovely. So let's try to do this now. Okay. So let's remove this flight fence now. And let's see. So let in flight semaphore. Well, timeline semaphore. And let's check this out. I mean, we could also do the same with image available and render finished and stuff, but I just want to get rid of fence if possible here because that's so clunky. Let's see. Okay, create semaphore. Well, basically it's very similar thing to this, pretty much. So let's do that. But we gotta add a like push next mutable vk set timeline semaphore type, I think, or time create info, I think. Builder semaphore type vk semaphore type. And there's binary khr, timeline, and timeline khr. So let's go with timeline. Because we're not using the extension, we're using, yeah. And what else? Yeah, I think that's pretty much it to actually create a timeline semaphore. And yeah, you also add the initial value, or you can add the initial value. So initial, oh, not here, basically here you could actually go ahead and add initial value to the timeline semaphore. Interesting. So I'm just gonna leave it as 0, and let's see if we could actually figure this out. Our synchronization primitive states consist monotonically increasing 64-bit value. Omnidirectional synchronization between device and host. So you could use it for device and host, which is why it can actually also be like like a fence. Oh, hold on. What? Oh. What? Hold on. I think I get this. Render finished semaphore. Actually, I probably only even need one here. In fact, I think. Yeah, only one timeline semaphore, which is render finished semaphore. Yep. And then you could basically use it for both as a semaphore in queue present and as a fence to actually wait for it. Exactly. Interesting. So let's first of all make this null. Fence null. Okay, that's the first thing. Second thing is this render finished semaphore hopefully maybe should be like, oh, actually we cannot. Yeah, we cannot here in queue present. You cannot use a timeline semaphore. You can only use a binary semaphore. So since that's the case, we need a second semaphore. So yeah, no, that wouldn't work. Let's just go with the separate one. That hopefully would work. So where's the semaphore that we have just created? Okay, let's see. Device create semaphore timeline. Okay, cool. So now what? Either binary, though the Windows system integration APIs are currently a notable exception. Important caveats also apply when a mixture of binary and timeline semaphores are used with the same for workflow, as we'll see below. Oh, okay. So a mixture of binary and timeline is kind of crazy. Okay, cool. So maybe that wouldn't work. Let's see. Squeezing them. Binary. Directly from the, oh, signaled from the host. Like, was the fence able to be signaled from the what? Interesting. Hold on. Device dot signal. Signal semaphore. What? We were able to actually signal semaphore all this time? Interesting. Or can be signaled directly. Okay, so that adds another dimension. So you could actually signal semaphore from the host now, which is very cool. Like Wikifig fence, they can be waited on directly from a host thread. That is very interesting. So Wiki wait semaphore, and this is the wait info. This is basically what we need here. S type wait info pnext null flag semaphore count 1, p values wait value, which is 1. So we're waiting it to become 1. Interesting. Here, when you signal it, you could actually give it a value that just basically should be greater than what is the previous value. Well, if that's the case, then how are we going to be able to do that? Yeah, probably binary fence is fine for this case, honestly, yeah. But this is very interesting. But yeah, anyways, I think I'm just going to keep the binary fence for now. Especially that here we're trying to mix both, so maybe that wouldn't be great. So yeah, so I think that's pretty much it. Let's just keep it as it was for now. Though later on, maybe when we have like multiple in-flight frames, maybe that would be useful. Anyways, I actually researched this off camera more. I didn't think it was like that interesting. Okay, let's remove this. Yeah, I think that's it for now. Let's make sure everything still works. Cool, great, lovely. So this is basically upgrade to sync 2, and also we upgraded the swap chain. Where is it called? Quar next image. Quar next image 2. That's basically what we have done. So yeah, we also added this cargo thing. And we have changed this. There's no need to honestly change this one, just roll back. This exact one, yeah. Main RS, vertex shader. Yeah, for this one, just roll it back. I just wanted to actually show you guys that little thing. And yeah, that's pretty much it. We also add this swap chain format here. Cool. Cargo channel. So yeah, let me just commit this one, and basically commit this one. Fix simver, ash simver, and yeah, commit. And that's, I think, pretty much it for this video. Honestly, it's been already 2 hours and a half. I think that's it for now. See you later. Goodbye everyone. Thank you for tuning in. Goodbye. Have a great day or good night.